All right, hey everyone. We're going to be talking a little bit about confidence intervals for a population mean today. I know this is probably things we've seen before. In fact, this was the notes that we had went over right before break, but I figured starting here would be kind of a good place just kind of get into the format, see maybe how things might be a little different, and also give us a little bit of a reminder. It's been, I think, a good solid 2 weeks since we last saw each other. So hopefully this is a little bit of a refresher for everyone. All right. So, I'll start with the definition. A point estimate is a single number that is used to estimate the value of a population parameter. So, we've been talking about is we have a lot of statistics that we can find and get, and statistics come from samples. But what we really care about are the things that are going on with the population, those parameters for the population. And so, what intervals are going to do for us is they're going to give us kind of an interval, a range, where we expect that most of the time using this method, we should end up having that actual population parameter somewhere in that range. So we have to use these point estimates to kind of help us try to estimate a value of a population parameter. And this is our starting point. So to estimate mu, which of course is the population mean, our best estimate is x bar. So another way of saying this is x bar, so our sample mean, is a point estimate of mu. Alright, so we want to know kind of how close x bar might be to mu, kind of where we might be looking for things, and so in order to do this, we're going to use these things in confidence intervals. So a confidence interval is a range of values determined by a sample used in order to estimate the true value of a population parameter within a given confidence level. And these confidence levels are percentages between 0 and 100% that are going to measure the success rate of the method used to construct a confidence interval. So if we say that 18.3 to 22.1 is a confidence interval of 95% confidence level for mu, then we are 95% sure that mu is between 18.3 and 22.1. So what do we mean when we say we're 95% sure? What we're saying is 95% of confidence intervals, move that up a little bit, that we create this way for mu from every possible sample of a certain size will contain the true value for mu. Okay, so in other words, what we're saying is that we're creating these confidence intervals. Typically when we use our method for creating confidence intervals, which we'll see in a second, we are basing them on our sample size in some way, and we're saying that most of the time, in this case 95% of the time, the interval we create is going to have the value for mu, and for our particular sample, that's true 95% of the time. Now, remember, samples, sometimes we get a really good sample, sometimes we get a bad sample, and so it's possible that we don't get a sample that has, or a confidence interval that has our population mean in it. So let's talk a little bit about our assumptions. So recall that for a large sample size, in other words, having a sample size greater than 30, the sampling distribution for x bar, our sample mean, is approximately normal with mean mu and standard deviation, also called the standard error, of the population standard deviation over the square root of the sample size. So when we're creating our confidence interval, and this will be true not just for the population mean, but for other things going forward, our confidence interval is going to be created by using our point estimate plus or minus our margin of error. So remember, our point estimate is going to be x bar, and our margin of error is going to be equal to some critical value times the standard error. Now, how we find this critical value will change a bit based on what exactly we're doing, but it's going to be a specific percentile that's related to our confidence level. Our standard error, as we said above, is the standard deviation for the population over the square root of n. All right, so let's talk about how we find some of these critical values and get some of these confidence intervals. So let alpha be any real number between 0 and 1. The notation z sub alpha is going to refer to a z-score with an area of alpha to the right. And the notation z sub alpha over 2 is going to refer to a z-score with an area of alpha over 2 to the right. All right, so why am I talking about alpha over 2s and alphas? So if we're trying to find a critical value for our confidence level, 1 minus alpha will be the confidence level expressed as a decimal. So in other words, if the confidence level is 95%, then alpha equals 5%, or 0.05. So since we're expressing as a decimal, instead of percentages, we'll use our decimal forms. So when we're looking at some sort of confidence level, basically what we're saying is, since we're looking at a normal distribution, we'll have an area of 1 minus alpha in the center, and then we'll have alpha over 2 as an area to the left, and alpha over 2 as an area to the right. So remember, those area under the curves are percentages for us. So here would be the z-score of negative z of alpha over 2, and here we would have the z-score for alpha over 2. So here what we're saying is, at this z-score we have half of this alpha here to the right in area. And so this is our confidence level as a decimal. So for our 95% confidence interval, we're saying that we have 0.95 in the middle, and on the left we have 0.05 over 2, and on the right we have an area of 0.05 over 2 as well. And so these z will be negative z of 0.025 and z of 0.025. So we want to figure out what those z-scores are in order for us to figure out what our critical values are. So remember that when we want to find these, we'll use inverse norm in our calculators. All right, so let's go through some examples. So suppose we've got a large sample that has a mean of 7.1 and a standard error of 2.3. We want to construct a confidence interval for the population mean mu with different levels of confidence. So if we're looking at 90%, we're saying that 1 minus alpha equals 0.9, and so that means that alpha equals 0.1. And so when we're trying to find our critical value, what we're looking at here is something where we've got 90% between these two cutoffs. We've got 0.05 on one side and 0.05 on the other as far as our area goes, and we have a z, negative z of 0.05 and z sub 0.05. And this is going to be what our critical value is. So this is how we're finding our critical value. So it's based on whatever our alpha or alpha over 2 is. So in order to find z sub 0.05, what we're going to do is we'll take the inverse norm of 0.9 plus 0.05. Now recognize that why we're doing this is we want to figure out based on the area to the right that's left. So when we're looking at the inverse norm, it takes the area to the left, it takes our mean, and it takes our standard deviation. So remember, for z-scores, the mean is 0 and the standard deviation is 1. So just a little bit of a reminder, if you're on, say, a TI-84 plus, we want to go to second, and then above vars is distribution, so distributions, and we want inverse norm. So that third one, INV norm, and then we want to put in our 0.95, or 0.9 plus 0.05, 0, and 1. And when we hit enter, we get roughly 1.645. So then our confidence interval when we go to construct that will be x bar plus or minus this z-score we just found times our standard error. So for us, it would be 7.1 plus or minus 1.645 times 2.3. And so that means that when we go ahead and make our confidence interval, we're saying we have 7.1 minus 3.8 on one side, so this is roughly 3.8. And mu's between that and 7.1 plus 3.8. And so our confidence interval is 3.3 to 10.9. And so we say we are 90% sure that mu is in this interval. All right, so that's just if we're looking at 90%. If we change from a 90% confidence level to a 99% confidence level, the only thing that's really going to change out of this whole formula is whatever the critical value is that we're looking at. So here, if we're saying that 1 minus alpha equals 0.99, then alpha equals 0.01, So alpha over 2 will be 0.005. So once again, it'll kind of help to visualize this a little bit. We've got 99% of the area under the curve in the middle. We get 0.005 over there, and 0.005 the area over there. And so we're interested in these z-scores. So when we're looking for z sub 0.005, it'll be the inverse norm of 0.99 plus 0.005, 0, and 1. And so that will roughly be, I want to use inverse norm, 0.995, 0, and 1. And that'll be roughly 2.57, we'll say 58. We'll keep it going. And so here, when we're trying to make our confidence level, that'll be 7.1 plus or minus 2.5758 times 2.3, or 7.1 plus or minus 5.9244. And so now our confidence interval will be 1.1756 to 13.024. And so here we would say we are 99% sure that mu is in this interval. Okay, so let's look at maybe another example, and then we'll talk a little bit about what makes us pick certain confidence levels and kind of some standard misinterpretations that we might have. All right, so let's say we're looking at the mean test score for a simple random sample of 100 students being X bar, which is 67.3. The population standard deviation of test scores is 15. We want to construct a 98% confidence interval for the population mean test score. If you've seen this before, or if you feel confident from the last two examples that you can do this, I encourage you to take a moment to pause the video, try it on your own, and then come back and see the results. All right, came back. So we know then that our confidence level is 0.98. So then alpha will be 0.02, and so alpha over 2 will be 0.01. And so once again, if we want to draw a pretty picture, which I recommend, we've got 0.98 in the middle, got 0.01 over here on the left for the area, 0.01 on the right. And so the thing we're interested in is z of 0.01. And so in order to find this, we'll take the inverse norm of 0.98 plus 0.01, 0, and 1. And so we'll roughly get 2.326 when we do that. And so when we want to construct our confidence interval, it'll be 67.30, so our mean, plus or minus 2.326 times 15 over the square root of 100. Now note that this time we weren't given the standard error, we were given the standard deviation and the sample size. So this is the standard deviation divided by the square root of the sample size. Square root of n. So keep that in mind when you're making your confidence intervals. We're using the standard error, not the population standard deviation. So when we do this, we should get 67.30 plus or minus roughly 3.489. So this is our margin of error. And so we should get 63.81 as the lower bound to our interval and 70.79 as the upper bound to our interval. And so we are 98% sure that the mean test score, that mean old test score, I'm just kidding, that the average test score is in this interval. So remember, we're talking about for this test overall. So not just necessarily in this sample. We know what the average was for this sample. We're looking at what we think the average would be over all possible populations, or all possible samples, looking at our population. If we had everybody take this test to fit our category for people who should be taking this test, this is where we'd expect the overall average to be in about 98% of the time. Now, the nice thing is that they were 98% sure we're in this. This isn't too bad of a range, somewhere between 7% or so, one way or the other. This is decently narrow. If we want to be more confident that our interval contains the true value, we have to increase our critical value, which increases our margin of error. So we have kind of a little bit of a Goldilocks situation here. So there's some trade-offs to make. So we want to be very confident, right? But if we're more confident, that leads to a larger margin of error. Commonly, people will choose 95%. If you need to have very high confidence, you might choose a larger interval, such as 99%. If you're choosing a confidence level in general less than 90%, you're usually not having something that's very reliable for practical purposes, and so you probably are not going to see something that has a confidence level of less than 90%. So the confidence level measures the success rate of the method that we're using to construct the interval. However, it doesn't measure the success rate of any particular interval. All right, so a little bit of an example to illustrate this. Let's say we've got some sort of hospital administrator who's planning to draw a random sample of 100 records of patients who were admitted for a cardiac bypass surgery. They're going to compute the mean number of days spent in the hospital and construct a 95% confidence interval for the population mean using an appropriate method. After drawing the sample, she concludes that the 95% confidence interval is 7.1 to 7.5. We want to talk about two claims here that someone might make. One person might claim that the probability is 0.95 or 95% that the confidence interval will cover the population mean. This is true. However, what it's not saying is that the probability is 0.95 that the population mean is between 7.1 and 7.5. This is not really true. We could have a bad sample. And so because this is a random event, we're not necessarily saying that 95% of the time the population mean's in between these two values. We're saying that 95% of the time the interval we create should have whatever the population mean is in there. So kind of a tricky distinction to make, so definitely ask a question about it during the live session if you're kind of confused. So far, we've kind of talked about and assumed that we have the population standard deviation, because we somehow think that we'll have the population standard deviation and somehow not know the population mean. If that seems like a little bit of a weird claim to you, it's because it is. So because we're looking at using the population standard deviation, our critical value is going to be based on z sub alpha over 2, because this is approximately a standard normal curve. However, if we're not using the population standard deviation, we don't know it, we're going to replace this with the sample standard deviation, and this is something that does not have a normal distribution. And so, because this doesn't have a normal distribution, typically what it means is we're going to end up increasing our spread, and so we have to use a different distribution that's called the student's t distribution. There are many different versions of this distribution, and each is going to be distinguished by its degrees of freedom. So when we're constructing a confidence interval here, our degrees of freedom, so for confidence intervals, the number of degrees of freedom is one less than the sample size. So when we get to a large enough sample size, enough degrees of freedom, the t distribution and z-scores are not going to be all that different. However, some things that we want to point out, for any t distribution, our mean is going to be 0. And t is going to end up being a little more spread out than the normal distribution. So the student's t distribution is symmetric and unimodal, which is, it's nice that it's those properties. It's more spread out than normal distribution, and if we increase our number of degrees of freedom, the student's t distribution in that curve is going to become closer to the standard normal curve. So when we don't know the population standard deviation, we'll use t sub alpha over 2 as our critical value. Instead of z sub alpha over 2. So that means we'll need to be able to come up and find these t sub alpha over 2's as well. So let's go through an example of doing that. Alright, so a simple random sample of size 10 is drawn from a normal population. So here, n equals 10. We want to find the critical value for our confidence interval. So when we're looking at our t distribution, finding the alpha is going to be the same. So we've got 0.95 here, and so this will be 0.025 on the left and 0.025 on the right. So we'll have negative t sub alpha over 2 and t sub alpha over 2. So then, if we want to find this t of 0.025, so that's what we have here. I think the camera maybe is working. Okay, cool. Something weird happened on my end. So hopefully it doesn't impact the video. We're going to use the inverse t function. And when we use the inverse t function in our calculator, we have the area to the left and a number of degrees of freedom. So degrees of freedom. So here, this area to the left is going to be 0.95 plus 0.025. So this area is to the left of this value. And our degrees of freedom will be 9, because remember, it's 1 minus the sample size. So degrees of freedom is 10 minus 1, which is 9. So if we want to do this in our calculators, we can go to the distributions. So this is what we did before, second, and then above this vars button, we have distributions. And then inverse t is right there, so we'll do 0.975 or 0.95 plus 0.025, comma 9, and we will get roughly 2.262 as our critical value. So this question was just asking for the critical value, so now we know how we can find that. All right, so some assumptions when we're creating our confidence interval, regardless of whether or not we know the population standard deviation. The first is that we have a simple random sample. So we haven't really talked a lot about sampling since the beginning of the semester, but we've been assuming in this class that we're using simple random samples. And we also want to make sure that our sample size is large, or we have approximation or a population that is approximately normal. And so our way of finding this is determining that, or we use these to determine that x bar is approximately normal. For this video, so let's say we've got a food chemist who's analyzing the calorie content for a popular type of chocolate cookie, and here are our numbers of calories in the sample of 8 cookies. So here, n equals 8. We want to find a 98% confidence level for the mean number of calories in this type of cookie. So here, notice that our n is less than 30. So we have to ask the question, is the population approximately normal? So look at our different calorie counts for these cookies. I'm just going to plot them out really quick. 112, 113, 114, 115, 116, 117, 118, 119. Oh no, I shouldn't have drawn this first. 120. There we go. We have a cookie at 111 calories, one at 113, one at 114, one at 115, two at 116, one at 118, and one at 120. So there are no outliers here, and no evidence of strong skewness. So we won't reject that this sample comes from an approximately normal population. All right, so with that in mind then, we want to go ahead and create our confidence interval. So create our confidence interval. And so this will be x bar plus or minus t sub alpha over 2 times s over the square root of n. So here we get our standard error by using our standard deviation for our sample, and we need to find our t sub alpha over 2. So here, x bar will end up being 115.375. For time's sake, I'm going to calculate that in S for you. 2.825 will be our sample standard deviation. And we're looking for t sub alpha over 2. Because we have a 98% confidence level, this alpha over 2 will be 0.01. And we'll find this by taking the inverse t of 0.98 plus 0.01. And our degrees of freedom will be 7 because it is n minus 1, our sample size minus 1. And so here we'll end up getting approximately 2.998. Taking all this information and using it to create a confidence interval, we get 115.375 plus or minus 2.998 times 2.825 over the square root of 8. And so this will end up giving us, in the end, that mu is between 112.4 and 118.4 as our confidence interval. And so we are 98% confident that the mean number of calories per cookie is in this interval.